For Learning Circles Flipping the Odds, we're doing essentially a webinar to give you a glimpse into the classroom of data science solving for real world challenges. This is a course that's going to be taught by Professor Harsh, with Gautam actually being the teaching fellow for it. Now, with this, I want to introduce the panelists for today. So we have Professor Harsh joining us, who's actually the assistant professor of biostatistics at Yale. And he has a background in computer science. He did his PhD there in computer science at Duke University. He studied in India as well, and he has a lot to share. Now, in terms of his introduction, I actually wanted to throw a challenge towards you, Professor. If you could actually explain what you're doing as your research work right now in one
Yeah,
sentence.
yeah. So if you want to make a decision, you want to make a decision that is data driven and not in blind. But how can you use data to actually allow you to make good decisions and not just rely on spurious correlations? So what in one the key word over here is causal inference. So I use like the causal inference methods to tell you what causes what and what kind of decisions are good in certain scenarios.
Thank you so much for the introduction, Professor. And I think that really breaks it down for everyone to understand. With that, we're going to have Gautam joining you as well, who's going to be leading the hands on activity today. And Gautam has actually TF'd with us for 3 times. So he's a veteran when it comes to Horizons Achievers program. He's been working on data science for a really long time. He studied at Ashoka as well. And Gautam, I want to throw the same challenge your way. If you had to explain your research in one sentence, how would you? And I know that you have multiple projects going on, so that's going to be a bit complicated, but I would just really like to hear from you anyway.
Yeah, sure. I think one sentence would be so if I want to make a decision regarding my health or anything that comes under this umbrella of health data, then how can I make my decision with like proper confidence with and without making sure that and making sure that I don't get many errors in the way. So yeah.
So we can really see this overlap between the work that Professor Harsh and Gautam are doing. And I'm really sorry if this is not technically correct, but that at the end of the day, it's focused on decisions and how you can really make them in a well-informed manner. And I think a lot of the work that we do kind of boils down to that. With this, I'm going to hand it over to the experts. So, Professor Harsh and Gautam, over to you. We're going to now walk into flipping the odds, which is going to be the activity today. It's a hands-on introduction to randomness, probability, and data visualization. It's also going to be an introduction to how do you make a decision as simple as if you flip a coin, do you call heads or tails? And if there's anything that we can actually learn more about it to be able to make more well-informed decisions where it seems to be entirely improbable to be able to do so. So over to you, Gautam.
Yeah, just give me 1 second. Um, Okay. So hi everyone. I actually named this session Flipping the Odds because I was actually planning to do something along the lines where all of the students or all of the high school students can intuitively get, but also it will introduce you to the idea of this randomness probability and how do you visualize something as simple as tossing a coin or get when you or when you toss a coin multiple times, then how do you make sure that the results that you're getting actually make sense? So that's the core idea or the core, I'd say the experiment behind today's session. That is, we'll take a coin, we'll flip it multiple times, and we'll flip it in different ways, and we'll see how we can infer different informations from this activity and how we can visualize it as well. So before I move ahead, I just want to make sure that the students that they have joined, they are familiar with some concepts of probability. Uh, you can just raise your hand if you know, or it's fine.
I'm sorry, I didn't get the question.
Are you familiar with some concepts of probability?
Yeah, with basic probability that maybe 10th grade probability, yes, nothing
Yeah,
beyond.
yeah. That's all that we want for today's session. So I think if you're familiar with that, then it's all gonna be fine. So just to sort of recap, so
Gautam, there is a question
yeah.
by Aaron. Aaron has a question, sorry.
Uh-huh.
I only know very basic probability, like the rule for mutually exclusive events and independent events. Uh, I don't know much probability, only very basic rules, that's all.
I think that's
That's
perfect.
that's that's more than enough actually for today's session. But the only thing I think that we'll need today is that if you flip a coin and it is a fair coin, then the chance of you getting a heads is zero point 0.5. I think that's all that we require for today. And moving on, Isha, can you move to the next slide? Yes. So the three things that I'll actually cover in today's session is are built around these three concepts of randomness, the law of large number, and then bias and signal. So in randomness, what we'll actually do is we'll look at how how flipping a coin or making one trial of a flip and how repeating it multiple times actually changes or actually gets you closer to the what a true probability would look like of an event or of a trial. And then continuing on that, we'll see that if we increase our number of trials and if we increase the sample or the sampling that we are doing, then how we I'll say like how do we move towards a more uh, ground truth that exists for that particular event. So for example, for a flipping a coin, we know intuitively that if we flip it, then there's a 50-50 chance that we'll get heads and a tails. But we'll also visualize it and do it experimentally. How if we flip it, let's say 100 times, then 1,000 times, then how do we move towards that number of zero point 0.5 that we usually know? So in a more data-driven approach. And then finally, what I'll cover is essentially the topic of bias and bias through the concept of, again, coin only that if we flip a coin, then let's say now we introduce a 70% chance that we'll get a heads instead of equal 50-50. And then we'll see how do we actually take this concept and identify that whether our data has bias coming in and whether the data that we are going to analyze later in the course actually is the fair data that we are looking. So, do any of you have any doubts till this point? Okay, then. Next slide. Yes, so what I have actually done for you, all of you, is for all of you to participate, I have actually created a Google Colab notebook. And in that, I have already written a bunch of starting code. You don't need to actually know much for the coding. Will only be changing a few lines or and a few numbers that will correspond to the number of trials. And then from there onwards, we'll see how running those code blocks as well, we'll visualize how the results look like. And this is just to provide you a glimpse of how the rest of the material in this course would look like and how building on top of this throughout the course will learn more techniques and more different ways to analyze the data and interpret all these results in a more meaningful way. And we'll also see that how when it comes to data science, uh, the actual concept that we need to follow is asking the right questions in the end, because to make the data make sense, we need to have the question that actually uh, ask for a proper solution. Yeah. So I think we have shared a link in the
Yes,
chat.
Gotham, we have
So
shared the
yeah.
link in the chat box. Do let me know if you need me to stop sharing my screen so that you can share yours instead.
Uh, yes, I think you can stop sharing. I'll
All right,
share
perfect.
mine.
I'm also excited to do the activity myself, so I'll be logging in
Yes.
from my mobile.
Can you see my screen?
Yes, it seems to be currently loading for me. How about the rest? can see it now.
Okay, so yes, so the steps that we'll be following is essentially I have already some code setup in the collab notebook that I'll share in a few moments. And then the first thing that we'll look is how is the law of large number. That is how if we increase the number of trials, increase the number of sampling that we are doing, we reduce the randomness, and when we move towards a more the probability that we know for a fair coin flip. And then we'll move towards introducing a little bit of bias, and then we'll at the end essentially visualize all of these results. So I can come back to, so you can come to the Google Colab notebook. And the first thing that you'll see here is, I think for all of you, it will be in a view only mode. You cannot essentially edit it. So what you need to do is go to the file, and you'll see option as save a copy in Drive. So this is what all of you need to click. And if you do that, what it'll essentially do is create a copy of the notebook that I have shared and open it in a new tab, essentially. And this will be your local copy, the that you will be working on alongside me. So if you have saved it to your drive, just give a thumbs up, and then we'll continue. Okay, I can see, yeah, Harsha and
Yeah, you're all
okay,
good,
yeah.
Gautam.
Uh-huh. Okay, so moving on. So what we have here is this is we have something called as a Jupyter notebook. If you know what it is, that's good. Otherwise, we'll also cover that if you are if you have taken part in this course during the first or the 0th week itself, and then we'll go over some very basics concept of how to quickly set up one yourself and then get going by writing your own code and start doing analysis. So what we have here is this will be again hands-on activity. And in this notebook, I have some pre-written code. And then there are portion in cells in between these codes where you will do the changes. So that I have highlighted with the double exclamation mark and a change keyword in brackets. So you'll clearly know where do you need to change. So what you can start with essentially is the first block, which is setup. And then you may, if you know programming, you may see a lot of these functions or these random English words, but uh, for right now, you can just press this play button and then it will run it. And what we are essentially doing is setting up all the material that we'll need to do the experiments, the flipping of the coin, the plotting of the results, and whatnot. Okay. So if you click on this play button, you should see towards the end setup complete and all helpers are ready. And if you are done till here, then we can start the next exercise, that is plotting, doing our first coin flip itself. So what we have within the first step is we are doing the first coin flip. And what you can essentially think of it as is N flips says the number of time we are flipping a coin, and P heads is actually the probability of getting a head in a coin flip. So this block essentially tells you is we are flipping a coin 10 times, and each time we flip a coin, we make sure that the probability that we get a head is zero point 0.5. But what we'll do now is we'll run this cell, and this will actually plot out a bar chart which will show the number of heads and tails that we got, and we'll see if it is actually 50% or not. So if we do this run, then we'll see that the first chart that we get actually says that we only get heads 40% of the time, and the rest 60% of the time we got tails. So and we did it with a fair coin. So our coin was fair. We didn't have any bias or any issues with the coin itself, but still we got essentially a 40-60 split here. But what it's telling us is you do a flip 10 times and there's a chance that you may only see heads 4 times out of the 10 times. But does that mean that the probability of getting a head is actually 4? Or is it just saying that we have not flipped it enough times? So this is what's the question that is being posed by this chart here is essentially. So just to quickly verify our results here, that what we'll try to do is we'll do this flip over increasing number of trials. So we started out with 10 and we got our 40-60 result. Oh, let's see, if I do it again, then I may also get a large amount or more amount of heads in our next iteration, because this is again truly random. We don't know how many times we'll get a head or a tail. We just know that if we do it enough number of times, then we may get close to the true probability, but that is 0.5. So this is our hypothesis, or our intuition says. So we can try it out by increasing this n flips, that is the number of flips that we are doing. So you can try it out yourself. Right now it's 10, then we can do 100. And if we do 100, let's see the probability. Oh, we can see that the heads is coming down and the tails is going a little bit up. So we are getting close to that 50% line. So let me try this again with 1,000 flips. And oh, we are getting more close now. So our heads is 0.5, 50.2 and tails is 49.8. And if we keep increasing our trials, so now we are on 10,000. So we'll see that we are getting even more close to the 50% range. And every zero that I increase, so now we are doing 100,000 trials. We are flipping a coin 100,000 times, a fair coin that has a probability of head 0.5. And if we do this, we can see that we are almost, or we have reached a 50-50 split of that we started, or that we guessed initially. So as we increase the number of trials, we see that we are getting closer to the true probability. So this is essentially the idea behind the law of large numbers. That is, if you bring out enough samples, or if as your sample number of flip grows, the proportion of head, or the proportion that we should see idle in nature gets closer and closer to the true probability, that was 0.5. And there is also a very so if you go to the next block, then you can see that so if we can also visualize this in a more of a line chart of how we sometimes see in a stock market, perhaps, that if we start with some n number of trials, and then it would get closer and closer to the middle in between, essentially. So again, if we start with 10, we can see that the probability of a head is jumping around. It starts from 1, hits 0.5 at 2 trials, and then it increases to point around 8, and then it decreases again, and then there's a lot of ups and downs here. And then if we keep increasing, so now we are at 100, we can see that it's getting closer to the line. And now if we do 1,000, we can see that we are now sort of reaching a plateau here, where the observed number of heads, or percentage of heads, is actually overlapping with the true probability, that is 0.5 here. So this is again the same experiment, the same data that we have, just visualized or represented in a different media, or a different format. In above, we were showing that if we do 100,000 flips, then we get a proportion of 50-50%. And in here, we again are showing the number of flips along another dimension as well. And we are just showing proportion of one result, that is the heads. And we are seeing that as we increase our number of trials, the percentage that we'll get is essentially close to 0, or equal to 0.5. So at 10,000 flips, you can see that we are overlapping with the 50% or 0.5% probability that we started with. And if we just do 100,000 just to match our code block above, and then we can see that this has essentially flatlined over 0.5, and this now represent the true probability, that is 0.5. So the idea that or the intuition that I want you to have is uh, getting or guessing the property by a very small sample size is essentially not correct for any of the trial or any of the experiment. So to get to the true answer, you need a large number, or a large number of trials. just to make sure that there is no randomness in your data that you're observing or analyzing. And we'll see more of these examples as we go along in the course, where we'll analyze the data that may have noise or that may not be related to true, but we'll have to work under some constraints or some assumptions there, just to make sure that the data we are working with fits under some criteria or some truth that we have defined. And so this is one example. And if any of you have a doubt till here, you can just ask or raise your hand, because next I'll be moving to the second concept, that was introducing a bias. Or you can give a thumbs up if it's all good.
Gautam, I have a question, actually.
Yeah.
Just pretending being a student. Why does the like when you showed 10 or 100, the number started above 50% line, then went down and then went up?
Mhm.
Why does that happen? Is it because when you toss more coins, there is more tail likely, or what is happening there?
So the the first data point or the first line that you saw where we flipped a coin and the dot was essentially on the one, or it could have also have been at the zeroth point.
I
So
see.
that was just telling us that if we flip a coin, then the number of output, the proportion or the percentage that we get heads can be either one or a zero. Because in one outcome, we can have either one head or a zero head.
So
And yes.
I'm again just pretending being a student, because this might be some of the questions that you have. What if we were to just toss 10 coins, but toss 10 coins 100 times? And then will that save us versus tossing 1,000 coins, right? Like, is tossing 1,000 coins same as tossing 10 coins 100 times?
Uh-huh. So, um, so what we are essentially asking is, if we take one coin and we toss it, let's say 1,000 times, versus we take 10 coins and we toss them 100 times. So, assuming that both of all of them are fair coins, then and we are just recording, let's say, one outcome after the another in a single line, then I don't think it would make any difference. Because you could think of the original experiment is you are performing it in let's say 10 different times of your day, and then each time you are just tossing it 100 times. So it would bring about to the same intuition.
Is there a real world scenario, Gautam, where I would see such a situation where I actually have to figure out if something is fair or not? Right? Like, can you like maybe give an example to me?
Uh-huh. Um, so, I mean, the one example that I'm getting is for uh, related to cards. But then if I'm playing, let's say, cards with someone, and I want to know if my sort of deck is not tampered with, so I would try to take out a card randomly and see if it is making sense. But then that would be actually a very big set, and I may not be able to verify quite easily. But
If you play
I
enough
have a,
games, you can, right?
yeah, I mean, yeah. I mean, if you can flip a coin 100,000 times, then sure, why not?
Yeah. No, I think, and I think there are situations like this, right? Right. Where imagine you go. This was back in when 2020 and 2021, when COVID was a big thing. I mean, it's still a big thing, but
Mm,
that and people used to go and get tested. Think of this as a coin toss event, right? Uh,
mm,
I mean, because all of these tests are essentially, in some sense, random. That they are chemical based, and they are not 100% sure that they are going to give you the correct answer. So there is some sort of randomness there.
mm,
And by just doing one test, you have to figure out if you actually have COVID or not, or you can probably do two tests or three tests, but after that you cannot.
Mm,
And so that I think that's one thing which jumped into my mind when I was looking at this is uh, what is the true probability that I have a disease, given that I have gotten myself tested, let's say 5 times, and four of them are negative. That means I don't, and one is positive, right? Something like that.
mm,
Uh, and again, that requires other things, not just if the test is random or not, right? Like the tests don't have 50% probability. They have slightly different
mhm,
probabilities, but that's another situation where you want to figure out the true probability by doing event again and again.
mhm.
I mean, that jumped to my mind. I mean, I think your card example is also very interesting. And
Uh,
definitely if you are aspiring to catch your friends in a game cheating, then you can definitely take that.
yeah, I mean, it is actually quite interesting. So, for example, if I want to, if I'm getting tested for some disease, let's say related to a liver or something, then and it comes back positive, then I would likely want my nurse to do one more test just to make sure that it's not a false positive in that case. So even though even though they did assure me that the rate that it predicts the correct outcome is pretty high, but still, so having more samples never hurts, I guess.
I don't know how much time we have, but I have one
Uh-huh.
last question. If I were to
Yes.
actually do this in practice, right? If I have a coin and I
Mm.
imagine I'm I don't know, Terminator in Sholay, and if I see you tossing a coin, right, and see Amitabh Bachchan always winning, how many times should Dharmender actually observe this event before saying that the coin is fair or unfair? Like how many coin flips are enough in some sense? Because you
Uh-huh.
said that you
Uh,
can keep on going, right? Like you can, I mean, right now you are at 1 lakh. You can do 10
mm.
lakh, 1 crore, right? I don't know. But when do you essentially say this is enough?
Uh-huh. We actually do have a section for that.
Awesome.
So
Thank you.
to
No, I'm
quantify
I'm
this
just
uncertainty.
I'm just priming you for future.
Yeah. Okay. Okay. If there are no question, then I think we can move on to the next section.
Yes, and I think
That
this is a great segue into what Professor Harsh asked as well, because from what I'm seeing, or from whatever understanding I have as a layperson, I think that's a biased coin. And
hmm,
while we would celebrate the biases while they're happening in Sholay, I think we would want to see how that plays out in real life.
yeah, yeah. So before we get to uh the point where we do actually quantify that uncertainty, or how many times do I need to flip, I think first we'll just quickly cover what a bias essentially is. So you can think of again the same coin, but it is now weighted one side. It's heavy on the one side, so it tends to land on that one side more. So that I think there's a doubt by someone. Yeah.
Um, Sorry to disturb, but in real life, how would you weight a coin without it being obvious?
Uh,
Oh,
How how would the
I
mechanism work?
I can give you an actual mechanism because I did it in my class. So you take a 5 rupee coin. I don't know if your generation has seen 5 rupee coins, and if they are still a thing. But you take a 5 rupee coin because it's thick, uh, and and then you just rub one of the side on your, nail cutters have filers, right?
mhm,
You just rub one of the side using filers, and you give that coin to your friend. They would not figure out it's biased, but that small change in mass on one side makes it land on the other side more often. That's one way you can make a coin bias. The other way is you can put a very small layer of wax, which you have
mm,
not, like it's almost invisible to naked eye. It's such a thin layer of wax. that also makes it biased, right? And every coin is biased inherently. It is impossible to have even distribution of mass on both the sides. I mean, if you think of like a 10 rupee coin, there is 10 rupee on one side, and then there is, I don't know, the symbol, the national emblem on the other side, or something like that. That itself causes some sort of bias. So that the bias might not be 70-30, but the bias might be 55-45. And in
Mm.
long run, that bias might play a role.
Thank you. And one more thing, is the is a coin toss an example of a chaotic system?
No, coin toss is an example of a random system. So a chaotic system is where two very close by starting points end up in a very different position, and the system can be deterministic, right? You take a very deterministic system, you take two starting positions very close to each other, physically close to each other, and after a long time, they would end up very far away. So that's a chaotic system. You cannot really uh, a priori say that small differences lead to small differences in the outcome. A random system is where you really there is randomness in the process. So if you toss a coin, you might get a head or a tail. But if you do it enough times and average them, they might actually converge to the same number. So a random system is different from a chaotic system. A chaotic system is a deterministic system where you have this property that 2 points nearby each other might lead to very different outcomes.
Thank you.
Mm. Uh, do anyone else have a doubt?
Gautam, I just wanted to interject and did want to
Yes.
mention that I think the bias section might be the last section that we're able to run and cover. So,
Okay.
in case you want to include any concepts from the later sections earlier on, please feel free to do so, just in the interest of time.
Okay. No worries. We can just cover the biased one, and I can, instead of finishing the rest, I can just quickly give a glimpse. I think that would be a good point to leave. So, yes, moving on to the bias. So, as said, we can introduce a bias by weighing down a coin, by adding mass or removing mass, or the idea of bias or weight essentially is that you have some outcome with a higher certainty or higher probability compared to other. So in this case, we have the heads will come with a probability of 0.7, and the tail will essentially come with a probability of 0.5, 0.3. So just to check this out, that does it actually make sense? We'll repeat the same experiment, but this time assign a probability of 0.7 to heads. And if we do a flip of 30 times, that we can see that we start off with heads around 76 and tails around 23. And as we increase the number of flips, we can see a similar pattern where the one bar is coming down, another is going up, and it's getting closer and closer to the original 0.7 for heads and zero point 0.3 for tails here. So around 10,000, we are pretty close, 70.1 and 29.9. And then similarly, around 100,000, we can see we have reached the point where we know that uh, the bias is being reflected here. And similarly, if we plot it over the line chart, we can see that, let me just write this up. Yeah, we can just see that increasing the number of trials will get us closer to the horizontal line of 0.7, which we now know is the true probability of heads, essentially. And around 10,000, it has been flatlined to the probability of 0.7.
Hi, Divya. I think you have a question. Please feel sorry, not Divya, Aaron. Please go ahead and ask.
Uh, Thank you. I noticed that when the graphs are leveling out, the one that's
Mhm.
decreasing goes a little lower than it's supposed to, and the one that's increasing goes a little higher than it's supposed to, or at least than the expected outcome.
Mhm.
So before suddenly seeming to realize that it's made a mistake and return and then going back to the expected outcome. Is there a reason for that?
It's just randomness actually. So by random, we started off with a point that we were having more number of heads, or and then there during the sampling of, let's say, 10,000 flips that we were doing, it does just turned out that heads were a little less than zero point 0.7. Just as we saw in the fair coin, that even though we have a 50-50 split, we still may end up with a 40-60 of heads and tails.
Thank you, sir.
Hmm. Okay, then I think this is pretty much it for the bias. And then you can actually play around by increasing or decreasing the bias here, that zero point 0.7, zero point 0.8 or whatever. And then you can play around with the number of flips and then you can see. The last point that I wanted to cover was uncertainty, but I think then we may not have a time. But the idea here was essentially that if we increase the number of clips, and so we may get our range for true probability may get shrink little by little and closer to the range around 0.5. So if we do 500 experiments and then within each experiment we flip, let's say, 10,000 times, then if we plot our results, then we know that our true probability lies somewhere between 0.49 and zero point 0.5. And if we do the same experiment with the biased coin, then we know that our true probability will lie somewhere between 0.69 to 0.71. So this was essentially the idea. And now I actually wanted to leave with an experiment of your own or a question of your own. So where the question actually states that imagine that a 60% of population have a respiratory disease risk factor. And so how large of a study sample do you need before you can actually reliably say that it reflects that 60% of the population that exists? So you can change the last block it's and just see what number comes up till all of your graphs merge or align, let's say. But yeah, I think this was sort of a wrap up for the hands-on exercise for today's webinar.
Gautam, if it's okay, can you keep sharing your screen and scroll up a bit? I actually have a couple of
Sure.
questions for you and Professor Harsh, and then I think we'll start wrapping up soon as well. So I remember the example or the question that you gave about, if it's a biased coin and it's being used in a scenario, when do you actually get to know it's a biased coin? And I was just thinking about it that let's imagine Virat and I place a bet and we decide to do 10 coin flips, and whoever gets the first five heads is the one who's going to win the money. And clearly, the probability from the graph states so that there's a whole chance that Virat will get first six as all heads. And that is actually a possibility, even though in my head, it's like it's an equal chance for it to be heads or tails in each of the trials. But I also vaguely remember that the probability kind of changes with each of the trials as well. So if you wanted to shed a little bit of light upon if there's any way we can really hack these bets, that's what I'm most curious about. Like, if I had to place a bet on a coin toss with someone, how can I really hack that without actually getting into applying the VATs or making the coin biased in any way?
So would you like to answer this one?
If the coin is truly fair, I don't think there is a way you can hack the bets, right? Because and again, assuming the system is truly random, you do not exactly have a secret computer in your pocket which calculates exact trajectory of the coin and etc. Right? If you don't have all of those, and if we assume that the system is actually random, like every time we toss the coin, there is some probability it's going to turn out head and tail, then no, there is no way you can hack the system. The only way you can hack the system is by creating a biased coin or like taking a biased coin, which is more probability of heads. And this kind of takes me to a segue. I think I'm allowed to give homework given that I'm a professor here. Maybe I think all of you have joined. Let's take a biased coin with 70% heads as the probability and 30% tails. That's the one that Gautam designed. What's the probability that you will get straight 3 tails when you toss the coin, right? This is absolutely doable with 10th grade math. And that kind of tells you, right? Like if I just take a coin which has higher probability of heads, but if I start tossing it, there is actually a very significant and non-zero probability that you might have 3 straight tails. And then you're like, wait, but this coin had higher probability of heads. What happened here, right? And so that's the idea of randomness. Randomness is that all and any and all reachable states are reachable eventually. Eventually, you will have systems where you have 10 straight tails, even if the probability of heads is high, right? So again, homework for you all. What's the probability that you will get 3 straight tails when you start tossing a coin which has 70% probability of heads? Yeah. So it's 0.3 cube, 0.027. Yes, Virat, that's the right answer.
I don't think you get to keep the answer and the way you arrived at it to yourself, Virat.
Just multiplying 3 over 10 cube.
Yeah. So every time you toss a coin, you want a tail, right? And the probability of a tail is 0.3 or 30%. And so if you want 3 straight tails, you need the first to be a tail that is 0.3, the second to be a tail that is another 0.3, so multiply, and then another 0.3. And so that's how Virat got to the answer. But basically, that's essentially saying that you have, I would say, 3% or 2.7% chance that you get 3 straight tails, which is actually not a small number if you think of it.
That leads me to my second question, Professor. We often come across tests, especially medical tests, that claim 98% accuracy, 99% accuracy. And if we are saying that 2.7% is not going to be a small number, especially when we're looking at randomness, then how do we really figure out the reliability of these tests?
Yeah, that's a fantastic question. So every test comes with uncertainty around it, right? And I mean, when someone says 98% accurate test, it means something. So I'm not going to go and define that because it's a little bit more technical. But let's say that 98, every time you have a disease, it catches 98% of the time that you have a disease, right? It is going to miss 2% of the times. And that is a serious probability. Imagine you were testing 1 million people. How many people, imagine you're testing 1 million people with a disease, right? Something like flu or COVID. How many are you going to miss out if you were to do that? You're going to miss out at least, I would say 20,000 or something, right? Which is actually not a small number. It's a huge number. And 1 million is not a big number. If you think of any Indian city, you have more than 1 million people in it, right? So if you're missing out 20,000 people every time you're testing, that is a huge number. So what people generally do and what clinicians generally recommend is do a double check. And sometimes you want to do the second check with another method, right? And so if you again go to COVID, your first test was this antigen test that you did with a small kid and kind of dipped it in it. And then if you came up with a positive result, you're like, well, is it truly that I have COVID or is it a random event? And so you would go and do a RT-PCR test. Again, I think the current generation is a little bit too young to remember these names. Like it's only been 5 years, but still it's a completely different era. And that test had much larger accuracy. The accuracy there was like 99.999% or something like that. And so you do the first round with a cheaper and less accurate approach. And the second round, if you come up with a kind of clinically relevant answer with something that is expensive and more targeted. That's how clinicians generally work.
And while I don't want to hog all of the questions, so that's why this is my last one, and I'll open it up to the attendees after this. I did want to ask, when we were talking about a coin toss, we look at it as a random event, but you mentioned the very real factors that don't make it random, which is that there can't be an equal distribution of mass. So if I were to ask you for real life example of a truly random event, would you be able to name one?
Truly random event. So I don't know how old are these kids. Do they know a quantum system? If you have studied quantum mechanics, that is truly random. There is the true randomness exists only in quantum systems. And then as you kind of get to like macroscopic levels, in aggregation, all the systems are pretty deterministic. It's just impossible to solve them. Like you think of weather, right? Weather systems, we have very good weather models, and you can solve the weather model perfectly to make prediction. The reason we have randomness in weather is because of something called chaos, which is what Aaron was going towards, right? That small changes in initial parameters lead to different outcomes, and we treat them as randomness. But truly, they're not random. They're in some sense deterministic, but we don't understand the full. Like we don't have computational capacity to do the full computation, and that's why uh, we see them as random. Aaron, I see your hands up.
Uh, yes, sir. So is there any system that is both random and chaotic?
Yes, all quantum systems are random and chaotic simultaneously.
Thank you, sir.
Are there any other questions that we have for Professor or Gautam today before we start winding up? This would be the last chance. I would really take it. I have a couple that I'm sitting on, but I'm trying to be conscious of time. All right. So with this, I'm going to pass on the mic to Virat. Gautam, I would request you to stop sharing your screen so that Virat can just take over and we can actually get a bit more insight into the data science course and maybe ask Gautam and Professor Harsh a couple of questions about the same as well, especially about what they're excited to go over in the classes. I think your screen is just loading and we should be able to see it now. Yeah, perfect. I would need you to unmute.
Right. Hey, so data science solving for real world challenges is going to be part of the Edition 2 of Ashoka Horizons program. Edition 2 is scheduled for June 20th to July 12th. Uh, in this course, as we can see, it's spread over 4 weekends. The live classes will take place from 11 a.m. to 1 p.m. on Saturdays and Sundays. You also have the chance to participate in office hours with the teaching fellow of the course, Gautam. And this is the breakdown of the course, which you can access on the website. Where week 1, we will go over very basic step, what is health data science, where we cover the broad overview. And in the project module, which will take place on Sundays, we will set up the Python and project setup. In week 2, we will work on prediction modeling, where we work on co-predictive models such as linear, logistic regression, decision trees, etc., and go over key concepts such as what is training versus testing data and evaluation metrics. In on the Sunday session of week 2, you'll get to play with the models, where you will fit one simple model, whether it be regression or decision tree, to the data and evaluate the metrics. In week 3, you will work on visualization and interpretation of your data. Uh, and in the project module, you'll understand and communicate the result that you've received in your session. And finally, we'll get to the demo day, which will be the final week 4, where the models that you've been working on throughout the program, you'll get to present them in the final day of the program. So I think we can get to the question about to the professor and teaching fellow about what they're most excited about in the course.
Gautam, do you want to answer first?
Sure. So I'm actually really excited to just deep dive into the hands-on session because it's it's sort of the most interactive part of the Horizons program. I get to interact with all of you one on one, and as well as we do like today we do a lot of coding together, and then we solve a lot of problems and on the fly, and it's very engaging and very fun. And I hope you'll enjoy it as well.
For me, I think one of the things which drove me to data science broadly was I can the whole idea of asking questions, and I think I'm inherently a curious person, and so what I'm excited about is kind of just discussing a bunch of questions with you, or like teaching how to ask questions which are answerable, right? Like we can ask questions, but we also need to figure out methods to answer them. And so like that's something that I'm very excited about, is kind of talking about how to ask questions, how to answer them, etc.
Thank you for sharing the professor. Continuing with the program, let me just show you guys. Give me a second. Yeah. So we have in total 9 courses offered in this upcoming summer cycle. Some are scheduled to take place in the first edition, which is from May 23rd to June 14th, and some are taking place in the second edition, which is a week after, June 20th to July 12th. The live classes, as previously said, are going to take place from 11 a.m. to 1 p.m. on Saturdays and Sundays. These are 30-hour courses spread across 4 weeks. And we're conscious of the fact that students in India have very academic schedule, and that's why we decided to spread these 9 courses over 2 editions. And you also have the chance to, if you would like, to attend more than one course. So if you're interested in data science, of course, you can go for it in the second edition. But if you're interested in a course that is taking place in the first edition, you can also opt to attend that. The link to the enrollment page can be shared in the chat box. And if you have any other question, you can reach out to us at horizons@ashoka.edu.in. The early application deadline is coming near. It's May 3rd, so it's less than 3 weeks away. So we encourage students to start their applications early, because we also operate on a rolling basis, which is first come, first serve. Yeah. If you have any questions, you can actually raise your hand and we will do our best to answer for you.
Thank you so much, Virat, for introducing us to Horizons Achievers program and the catalog for this summer. But most importantly, thank you, Professor Harsh and Gautam, for actually walking us through what randomness means today and what is truly random, what's not truly random. And I'm beginning to realize that we need to go beyond microscopic levels to be able to experience a fully random event. And that's gotten me thinking that I'm not going to be placing any bets on coin tosses anytime soon, especially with Virat now that he has the knowledge of making biased coins. So thank you so much for that, Professor Harsh, as well. I did want to open the floor up to any questions in terms of the concepts that we covered today or the program as a whole, because we'll be wrapping up soon. I know that you guys have taken out the time for the last 1 hour. I hope it's actually proven to be as interesting as you thought it out to be. And I'm very excited. I'm glad to see the very excited nods that I have witnessed. So thank you all for taking out the time, especially Professor Harsh and Gautam. And I hope you both feel better soon. I hope there's 100% chance that you're going to get well really very soon.